Hello everybody, welcome to the course on quantum theory of many-body systems in condensed matter here at the Institute of Physics at the University of São Paulo. My name is Luis Gregorio Dias, and in today's class we're going to study the non-interacting electron gas. This is a very important topic. Later in the course we're going to study the interacting electron gas, so it is really important to set up the stage here in terms of basic concepts on this topic, such as the Fermi energy and the density of states. So in today's class we're going to cover all that. We're going to start with a Jellium model and see how it translates to an effectively non-interacting model for electrons, for fermions. And then from that we can calculate the Fermi energy and the density of states. For instance, we're going to cover the density of states in 3D in this class, and as an assignment you're going to calculate the density of states in 2D. Alright, so let's go into the class now. Okay, so let's start with a model for electrons in a metal. So typically in a metal you have the atoms forming a lattice, typically, with some ordering, right, long-range order in terms of how the ions are located. So we're going to disregard these ions moving around, so we're disregarding phonons, for instance, and we're only interested in what happens to the electrons. So you have the positive charges, and you have in the atom you have typically two types of electrons. Some that we call the core electrons, which tend to be very close to the nuclei, but they are not really screening the whole positive charge for the nucleus, right? So you have these other electrons which are a little bit farther away, which sometimes you call them valence electrons, or just the electrons that are essentially responsible for the electronic properties of the metal. So typically in metals, say in the first column of the periodic table, we have one such electron, unbound or very weakly bound to the nucleus per atom, one or two, depending on which column of the periodic table you're talking about. But in any case, you have these core ions, and in our model, we're going to assume that they just sit there, right? They have these positive charges, so that the whole thing is charge neutral, but they essentially form this background, like a homogeneous positive background, right? And then the conduction electrons, they move more or less freely over this positive background, and moreover they weakly interact with the other electrons. And how does this come about? When you talk about Fermi liquids, this is going to be more clear. But for now, let's say that there's strong dielectric screening, so that the Coulomb repulsion is not long-ranged as it is in a bare setting, say in vacuum. But here, because of the presence of these other charges and etc., this Coulomb repulsion between the electrons is very short range. In fact, we can safely assume that in a model that the electrons are not interacting with each other. And later in the course, of course, we're going to look at how corrections due to electron interactions arise, and we're going to study that. But for now, let's do this Jellium model where you have just this free electrons moving in this positive background. And of course, the whole system is charge neutral, so it's really important to have the background so that you don't have just a bunch of negative particles, and you have actually a neutral system. So if the electrons interact weakly with each other, then we can describe this, at least the electrons, as a Fermi gas. So weakly interacting fermions in in a system, in a given volume and a given number, right? Number of electrons per volume, so with a given density. And the density is going to be crucial for us later, okay? Okay, so let's start with a single particle picture for this free fermion gas. Let's start then with a single particle hamiltonian. We discussed about that in the other classes. So in this case, the hamiltonian, the single particle, is just going to have this kinetic energy for the electrons. And here I'm using m star to represent the effective mass, and we discussed that in the very first class of the course, how the mass of the electron in these materials is usually not equal to the bare electron mass, but has a smaller value. But this essentially fits the idea that we have these free effective fermions. So the free equation for a particle of mass m, single particle, is just the kinetic energy times the wave function equals the energy. And we know how to solve that. The solutions for this are just plane waves with a given wave number k, a wave vector k. Here we're talking about 3D, of course. Then we have three components for this k vector, kx, ky, kz. And then each of these states is labeled by k. So this is a good quantum number, right? So it is, and the momentum is just h bar k. So this is a good quantum number related to momentum. Here I'm not going to go over the effects of the lattice here, but if you've already taken a course on solid state physics, you might know that this k in that notation becomes the crystal momentum, not exactly the canonical momentum. But things behave much more as they are here. There we have Bloch's theorem. We're not going to go into that right now. Let's just assume that the solution is just plane waves, okay? And we know how the energy depends on k, because replacing that, this is the absolute value of k, right? The modulus, the norm of this vector. So the energy is quadratic with k. So energy is h squared times k squared divided by 2m star. All right, so that's the plane wave solution, particle in a box. And instead of putting our electrons in a finite volume, as sometimes is done, we're going to consider periodic boundary conditions. And this reflects more or less the nature of the periodic potential that in the metals actually is there. So how do these periodic boundary conditions work? So let's say that you have your plane wave function, right? Instead of putting a constraint that it has to be 0 at at position 0 and 0 at Lx and quantize these numbers, we're going to quantize them imposing a different set of boundary conditions. It means that if you have, say, a volume of sizes Lx, Ly, and Lz, we're going to impose that this wave function follows these conditions. When you have x plus Lx, it should be equal to the wave function evaluated at x. Same thing for y and z. So let's take the displacement in x here, for instance. So you have this Lx, 2Lx, 3Lx. Every time you say you were sitting here at this position x, what I'm imposing is that the value of the wave function is the same if you are at xLx, x plus Lx, x plus 2Lx, x plus 3Lx, etc. That's what I'm imposing. I'm imposing that the function repeats itself every time you are in one of those boxes, right, with size Lx. And that happens in 3 dimensions, so it happens at y, and it happens in the z direction as well. So if I do that and I look here, what I'm telling you is that if I have a displacement capital L, which is just a vector in real space with components Lx, Ly, and Lz, that means that this has to be equal to the wave function at R, right? So if I have this plane wave solution and I displace R by L, what I gain here is a phase, e to the I k dot L. So if I want to impose that this function is equal to phi of k at position R, this extra phase has to be 1. And if this extra phase is 1, then our values of k, kx, ky, and kz, they have to be quantized, such that the sum of kx, lx plus ky, li plus kz, lz has to be an integer times 2 pi, right? Meaning that we have 3 indices here. This m will be a sum of 3 integers, right? Because this has to happen for not globally, but for each individual k, right? Because we're forcing this periodic boundary conditions on all 3 directions independently. So this m is going to be a sum of 3 other integers, and the sum has to be, of course, an integer. So these are 3 indices that will be related to k. All right? And then one solution for that is that kx, of course, is 2 pi nx over lx. That's one solution. Ky, same thing for ky, same thing for kz. So these guys will be not a continuous variable, but a discrete variable which is spaced by 2 pi over lx, 2 pi over li, 2 pi over lz. So that's the typical quantization of k when we impose these boundary conditions. Okay, so what do we have now? We have these discrete values for kx, ky, and kz, and as I said, they are going to be in units of these 2 pi over L, or the given L in each direction. So let's look at kx, for instance. It's going to be 2 pi over Lx times an integer, 0, 1, or 2. So if I look at, if I plot where these states are, they are labeled by a kx. So if I put kx on an axis, and I then look at the states here. So I have this states with nx equals 0, and x equals 1, and this distance here is 2 pi over Lx. Nx equals 2, and x equals 3, and the same for negative values of nx, minus 1, minus 2, minus 3. All right, so I'll have this same grid for ky, right? So I have ny equals 0, and ny equals plus 1, plus 2, plus 3, minus 1, minus 2, minus 3, and the distance here is 2 pi over ly. And if I would plot in kz, I would have the same thing, also a grid. So what you're looking at is like this 3-dimensional grid where each point is a state, is a possible state where my one possible single particle state that I can occupy with fermions, right? So for each of these points, there will be a wave function, right? It's going to be this plane wave function, but plane wave-like wave function. But remember, this k vector is quantized, right? So this wave function will, by construction, follow the boundary conditions that we impose, these periodic boundary conditions. But the fact that K is quantized also tells me that energy is also quantized here, right? EK is proportional to K squared, but this is Kx squared plus Ki squared plus Kz squared, and these are given by that. Now, let's see what this represents when you try to calculate the number of states, right? When you try to count these states. Notice that if I take Lx or Ly to infinity, the distance between these points go to 0. Then I recover, as I should, the continuous limit. But given that these guys are discrete, I can talk about the volume that each of these states occupy in K space, right? In the reciprocal space, in 3 dimensions. So what would be, if I can think that the volume for each of these states is like a small cube of sizes 2 pi over Lx, 2 pi over Ly, and 2 pi over Lz. So the volume of this cube is 2 pi cube divided by Lx times Ly times Lz, which is the volume, the total volume in real space, right? So this is the volume for one of such states, but I have many of them. I have to add the volume here in K space, and I know the volume of one, so I can see if I have a volume here in K space, and I can count how many states are there just by dividing the total volume by the volume of each state. So the number of states will be this, precisely that. For a given volume in K space, the number of states will be this volume that, I know, the integral in d3k divided by the volume for each of the states. So that's should give me a number, right? An integer number. And of course, this will be my sum over K for this given volume. Here, this K here is restricted to this volume in K space. So for instance, if I take a cube here, I would have these states here, and that would be my volume. I divide it by the volume for each particle, and I get the total number of states. And then there is this trick that we're going to use quite often throughout the course, which is how to use this to go from the discrete form to the continuum and back. Meaning that here, notice that the sum in K equals to the volume times the integral of d in d3k over 2 pi cube. So we can relate 1 over the volume times the sum to the integral in d3k divided by this 2 pi cube. Notice that this 2 pi cube is really important. It comes from the volume for a single state. So whether we want to take the continuum limit or the discrete limit, we can go from one to the other by replacing the sum with the integral, but remember to divide by the volume and also divide the integral in K by 2 pi cube. If you are in 2D, it's going to be 2 pi squared, and here is going to be an area, but the idea is pretty much the same. Okay, so we are now in a position to talk about the n-particle Hamiltonian. Given the single particle case that we have discussed so far. For that, we need to, in fact, double the number of states by including the spin quantum number, meaning that for applying this single particle states to a state with indices k, vector k, and sigma gives me the energy Ek, which does not depend on sigma. So up and down are degenerate states, but here I have essentially double the states that I had before, right? And this single particle state is the result of acting on the creation operator with indices k, remember this is vector, and sigma to the vacuum. So this is my single particle basis, so to speak. The n-body Hamiltonian is just going to be a sum for the single particle ones, and we learned in the last class how we write that in terms of these creation and destruction operators. This is just going to be a quadratic form, which is diagonal. So this is diagonal Hamiltonian. These are the single particle energies. And this is the many-body Hamiltonian. Remember, we're summing over k and also over the spin, sigma, right? And this, of course, is the number operator, which we discussed. And it counts the number of electrons at state k, right, the orbital, those little dots we had in the previous slide, with spin sigma. And we know that for each k, only 0 or 1 fermions or electrons in this case, with a given spin can be occupying that state. But since we are, of course, have this double degeneracy, I can always populate nk up equals 1 and nk down is also equals 1. So we have, if I add over spins, we have 2 electrons. But it's only 0 or 1 fermions per state, including the spin index. And now we go to occupation number basis, occupation number states, right? And we have here nk up, nk down, this Hamiltonian acting on this and the states will give me precisely that. Sum over k and a sum over sigma, which is precisely that times the state. So this is an eigenstate of this n-body Hamiltonian. And also, for now, we're going to consider that the total number of particles is even. So I have an equal number of spin up and spin down electrons. So we're talking about a non-polarized gas, right? So I have an equal amount of up and down electrons. So this is reflected in this sum. N over 2 equals sum of k over k and k up. And this should be equal to this sum of k and k down. So this is, we're essentially restricting, right? We could have the case where the sum is not restricted to n over 2, so this would be unrestricted if you want. So I could have polarized ground states, right? This is something that you might want to study when you have, say, models for magnetism, which include, say, an energy which depends on spin, say a Zeeman splitting or something. This could be interesting, but here we're going to focus on the non-polarized gas. N over 2 spin up particles, N over 2 spin down, so the total spin of the gas is 0. That's the point. All right, so let's talk about the ground state for this n particle system. So we now have how many the single particle states. They're labeled by this index k, a vector. So this vector runs from, say, k equals 0 right at the center at k space, right? And I can have either state up and a state down there. So you can think of two meshes put together in there. So each point has, is actually 2 points, one for spin down and the other for spin up. And then we can run over this index k, right? And this will give me the energy for that configuration. So say if I have only 2 particles in my state, the energy would be 0 because I'm only putting two particles on the k equals 0 state, so the energy is 0, so I would have 2 zeros. But then I can put 1 in, say, k equals 2 pi over Lx, and maybe another one there. So now I have the energy of the n particle system a little bit higher. So given a total number n, I will have the lowest energy for the n particle state given by this, right? Given the individual occupations of each of these states. So that would be the ground state, right? So you just are filling the states. Let's go back to the mesh so that you know what I'm talking about. So these are my single particle states. Remember, I can put particles with up and down. So if I have, say, let's count here, say 2 plus 2, 4, 6, 8, say if I have 10 particles, right? 10 particles. So my capital N is 10. What would be my ground state? So I can put these 10 particles in any state here, in principle. But that will not give me the lowest energy. The lowest energy is if I start filling up from the lowest energy state, which is right in the middle. I put 2 particles here, one spin up, one spin down. And then I go over to the next energy state, which are these 4 here. Why? Because this is nx equals 1 and ny equals 0, or the other way around, ny equals 1 and nx equals 0. But here that gives me an energy which should be h squared over 2 pi over L x. I'm assuming Lx equals Ly here, right? 2 pi over L squared divided by 2m star. So that's the energy of these states here. So they have the same energy, so I keep filling, right? But 2 here, 2 here, 2 here, 2 here, 2 here, 10 states. That would be my ground state for the n particle system. And I can keep doing that by, if I increase the number of particles, I keep just filling up these states. And in each state for a given spin, again, the occupation is going to be only 0 or 1. But, you know, I stop filling. All right, I might, for a given n, I stop at a given total energy for occupations given by the sum of the occupations of these states. And that's going to be my ground state. And the total number, of course, has to be capital N. This is an integer, and this is the number operator, which is just the sum of the individual single state numbers, right? Ck sigma dagger, Ck sigma, summed over K and sigma. That's my ground state for the n particle system. And what's going to be my ground state energy? Well, I have to add all the energies for a given K point and multiply it by the number of particles we spin up and spin down at that K point up to the last filled state, or even half filled state. But it's always going to be a filled state because we're assuming n over 2 equals the number of spin up electrons, and that's going to be equal to the number of spin down electrons. So to calculate this, we have to just do the sum where the value of k, the absolute value of k for the last occupied state in the ground state is going to be the Fermi wave vector. That's the definition, right? In that example that we have 10 particles, again, I have, the Fermi wave vector would be 2 pi over L. That's my Fermi surface would be just these 4 points here. These would be field states, right? Okay, so one more comment here, and from that we know that all states below or equal with k below or equal the Fermi wave vector are filled, and all those states with k above the k fermion in absolute value will be empty. That's the definition of my ground state if I start filling, of course, from the bottom up, and I'll stop to a point. Now there will be a you know, if your number, say, instead of 10 electrons would be 11, then I'll have to put these extra, well, not 11, I have to have n equals a pair. So if I had 12, I would have to put these extra 2 electrons. Going back to my mesh, I have these 10, and okay, I have 2 more. Then the next states in line would be one of these 4, right? Okay, where do we put them? It doesn't matter. The ground state here will be degenerate. Whether I put them here or here or here, you know, it's going to be the same energy, so it doesn't matter. Of course, if Lx equals Ly, then it might. The energies here will be slightly different, but if they're not, and usually we treat them to be equal, then they would be pretty much the degenerate. So then my Fermi wave vector will go here, and I know that for k larger than this, so square root of 2 times 2 pi over L, then everybody else will be empty, but there will be some empty states with k equals, with a wave vector of k equals kf as well. So this is, you know, this like a unclosed shell. So you might want to, you know, if you're not in the continuum limit yet, there might be some situations where you have k equals to kf, but they're empty. But you know, just it's just a detail when they're not filled. When you go to very large values of n and very large values of the volume, so that the spacing between the states is small, then these exceptions are much rarer. All right, but that would be then my ground state, and the n over 2 would be equal to the sum over all the occupied states of their occupation for these. So this should give me n of 2 for up, and for down electrons should all be equal to n over 2. Okay, so let's talk about the Fermi energy. And we notice from before that we defined already the Fermi vector, right? It's just the kf for the last occupied state for a given number. And notice here that as the number increases, kf also increases, right? And now the question is, what is the energy of the last occupied state? Or the energies, right? Because for a given kf, the energy, the single particle energy it defines a sphere in k space, since the energy depends on the absolute value of ks, not on its direction. So any state with the same wave vector in absolute value has the same energy, right? So that's what we call the Fermi energy, the single particle. And this is important. This is not the energy of the gas. This is the energy of the state, the single particle state, which is last occupied, right? So this is a single particle energy of the last occupied states. And of course, this will be as a sphere in k space, since the energy goes with h bar squared times k absolute value squared divided by 2m. So we can invert that and give you the Fermi vector in terms of the Fermi energy. So given one I have the other, right? So how do we calculate this in terms of, say, the density, the number of particles per unit volume? And here how we start doing these calculations given the ground state for the non-interacting Fermi gas. So remember, in each occupied state with K below Kf, there are 2 fermions on each state by construction, right? We use, and even in, we're talking about a non-polarized gas. All right, so for n fermions, I know that, let's pick one of the spin components, say up. I know that n over 2 is going to be the sum over all states with K less or equal than Kf, which are occupied, right? And of course, then n equals twice that. So I want to do this sum. And here's the trick that we did where we can replace the sum by that integral. And of course, by definition, if these states are occupied, then nk up is 1 for at the ground state. So this is 1. So this is just the sum, right? K over Kf. And we can now transform this into an integral. If I'm talking about a very large volume, meaning that 2 pi over L is very small, so the distance between these points is small, and I can take the continual limit. And then this integral should give me n. And remember the point here that this sum 1 over the volume on this times the sum is the integral divided by 2 pi cubed. Remember, I ask you to remember that. That's precisely what we're using here, right? So we can transform the sum in integrals going to the continuum limit. So let's do this calculation on the blackboard. All right, so let's then repeat that thing that we just wrote, that n equals 2 times the sum over k less or equal than the Fermi wave vector. And that trick that let me write over here, perhaps a little bit above that discrete to continuum it's 1 over the volume in real space times sum over k goes with the sum over d 3k 2 pi cube, right? So the sum is 2 times the volume times this integral of the 3k in a sphere of radius kf, right? Why is that? Remember, again, here we're talking about if we are in k space. Oops, sorry. So if we are in k space, we have this, and we have this sphere. What would be a good color here? Perhaps green, perhaps. And all the states inside are occupied. So this would be my kf. And all the states outside are non-occupied. So I want to get the volume of this sphere here. All right. So let's go back to the calculation here. Let's see. Okay. And this would be 2Vr times the volume. Okay, there's this 2 pi here times the volume of that sphere. So that would be 2Vr over 2 pi cube times 4/3 of pi. The radius is kf cubed, right? All right. So that should be equal to n. And remember that the Fermi energy is h bar kf squared over 2 times the mass, right? Okay, so let's continue that. So n equals, there will be an 8 up here, 2 times 2. There will be an 8 below, a pi cube below. There's going to be a 1/3 here, this one. And there's going to be VR, and I'm going to transfer the VR here. So this is going to be the density particles per volume, right? Okay, and there's going to be a kf, kf cube. So this goes away. There's these 2 already taken into account. That's all right. So this is the density of the gas should be kf cube 3 pi cube. All right. So, but that's not enough for us. We want to write this in terms of the Fermi energy. So I come here and I get kf equals square root of 2m star EF divided by h bar squared. That's 1. And so this is going to be 1/3 pi cube 2m EF h bar square times 3.5, right? This cube. Okay, now we're getting to something here. All right, so I'm going to now isolate the Fermi energy here and try to write it in terms of the density. This is the density right there. All right, so let's continue. So the first thing I do is I multiply the density by this 3 pi cube. And then I take this to the power of 2/3. And that should be equal to 2m star EF over h bar squared. Is that it? Yes. So that gives me that EF equals h bar squared over 2m star times 3 pi over cube, which is just constant to the 2/3, times the density at 2/3. All right. So important message here: if I increase the number of particles and keep the volume constant, I increase the density. If I decrease the volume and keep the number of particles constant, I decrease the density. In any case, the Fermi energy will behave as a function of the density, as the density to power 2/3. That's an important result here that we get from this calculation. Oh, just one other point here that I think I'm missing this factor of pi here. There should be a pi here, right? Then the actual power of pi here should be 2. Here 2 and here 2. Let's just correct that. 2, 2, and 2, so that, all right, here as well, so that we don't carry this extra pi around. All right, yeah, so, but again, the density, the Fermi energy depends on the density with the density to the power 2/3. Okay, so let's go back to the slide. So this is the calculation we did. K, the density is kF cubed over 3 pi squared, right there. We had that. And then we calculate the Fermi energy and show that it depends with the density to the power 2/3. All right, now we can talk about the ground state energy of this n particle state, right? So you have all these states filled with n particles, and we can calculate the energy, the total energy now, not the Fermi energy, the total energy of the gas, right? So how do we do that? Essentially, we keep adding the energies for each of the individual states for which are filled. So we just do the sum over K less than or equal to Kf of the energy times the occupation. And here I'm multiplying by 2 so that I'm taking, consider only, say, spin up. And that, for sure, these states are occupied by definition, so this nk up is 1. So I'm summing over K less than Kf of the energy of each state, K. Right, which depends only on the absolute value of K, so this is okay. Now we do the trick of converting this sum into an integral. So the sum is VR times the integral of d3k over 2 pi thirds, and in here this is the energy in terms of K. So we have to do this integral in a sphere of volume Vk. So let's go to the blackboard and do just that. Okay, so we're back to the blackboard. So this is our calculation for the Fermi energy. And from here, I want to keep at least this result here. Oops, sorry. This one. Okay. So let's do that. And remember that the density, what's written above, is the density is Kf cubed over 3 pi squared. Kf cubed over 3 pi squared, and of course EF is h bar Kf so over 2m star. All right, so what is the calculation that we want to do? E equals twice the sum over K less than Kf of Ek, and this is going to be 2 times the volume, an integral of the energy, which is h bar K squared 2m star over 2 d3k over 2 pi cube, right? And this is over that sphere radius Kf. All right. So the integrand doesn't depend on the angle. So right off the bat, we get a 2 pi here, a 4 pi, right? Integrating on the angles. And now we're left integrating over the radius. Kf. Of what? This Kr. K squared 2m star, and of course this, right, remember, it goes to K squared dk times the integrals in the angles. So we already did the integration over the angles, so I am left with a K squared dk here. All right, so let's just do this integral. So there will be that 8 pi on top times the volume. there's going to be, oh, there was this 2 pi cube here, right? Cannot forget that. That's going to be 8 pi cube. So already we have this cancellation here, 2, this goes, and there's a square here. There's going to be an h bar squared to m star, and we're left with 0 kf k to the 4th dk. Right? Okay. 0 to kf. So this is k to the 5th over 5 between 0 and kf. So this gives me, let's go back here. So there's going to be this VR times h bar square. There's going to be a pi square here, 2m star. Am I missing something? No, that's it. Times kf 5th over 5. All right? Okay. Now, let's remember here that this is so kf cube, that this is going to be important. Kf cube equals 3 pi square times the density. All right, so let's remember that. Okay, so this is VR h, and I'm going to put this pi square. There's going to be these 3 of these 5. I'm going to join and substitute by 3 pi square times the density. Okay, and the other 2 I'm going to put together with h bar square over 2m star. All right? Okay, why did I do that? Well, so that things are neat now. So remember, we're calculating the energy. All right. Okay, so this, let's cancel some things out here. This pi square goes away. This density is just the number of particles divided by VR. So this VR goes away with this VR. We're left with the number of particles here, okay? And this is precisely, if you remember, the Fermi energy, right? All right, so that's great. We there's a 5 here missing here, right? So there is this 5 here that I have put here. So there's this 3, 5 n, right? This is left times the Fermi energy, and that's the neat result, meaning that the energy per particle, this is the total energy of the ground state, right? This is the total energy. Let's emphasize that. This is important. Total energy. So it has to increase with the number of particles, right? But so if you keep increasing the number of particles, you keep adding, particles to my ground state, and the energy increases. But if I calculate the energy per particle, that's 3/5 of the Fermi energy. So that's not the Fermi energy, it's 3/5 of it. So this is an important result. Okay. Right, so this is, remember this is important, the energy per particle. So coming back again to the slide, let's keep going. So we did just that calculation in the blackboard, and the energy per particle is 3/5 of the Fermi energy. And typical values for those. So in metals, in general, Fermi energies are of the order of electron volts. So it is essentially 7 electron volts, 5, depending on the metals. So if I convert that to temperature, that would be like 80,000 degrees Kelvin. What do I mean by that? It means that this is sometimes called the Fermi temperature, right? So for temperatures which are much lower than that, such as room temperature, it is almost as everything happens at T equals 0 for the electrons near the Fermi energy. So the temperature dependence for the electronic parts of a metal are not really relevant here at room temperature. There are some deviations, but let me emphasize that relative to these typical energies, room temperature is a small parameter, right? Okay, now we can define 2 pi over kF given energies in this range to obtain a length scale, which is sometimes called is generally called the Fermi wavelength. So typically this would be like the de Broglie wavelength for metallic electrons, right, for these fermions, which is of the order of a few angstroms. This means that this is, these electrons, you only feel quantum effects for confining, for instance, if you are taking potentials which are a few angstroms apart, which essentially is right down to the atomic limit. So this means that it's very difficult to confine these metallic electrons, and we'll come back to that. But the other important thing is that what is the momentum, the typical momentum for these electrons, or the velocity, the Fermi velocity. This is another important parameter. So if you calculate that with typical effective masses for metals, this gives you about 1.5, 1.6 to maybe a factor of 2, 3, 4, but 10 to the 6 meters per second. That's 3 orders less than the speed of light. So this here is important. This is essentially the reason why we don't consider relativistic effects in our fields. So we're doing Schrödinger's equation, not Dirac's equation. That's the reason. And this is going to break down when you talk about Dirac materials, such as graphene, where not really that the Fermi velocity approaches the speed of light, but the dispersion in terms of energy against k is very much like those of Dirac particles, with Dirac massless particles like photons, right, or neutrinos. Not photons. Photons are bosons. So, but for now, for metals, regular metals, it's just non-relativistic free fermion gas. And one point that's really useful, to do these conversions, 1 millielectron volts is 11.6 Kelvin. So 1 electron volt is 11,000, right? That's the typical conversion, 11,000 Kelvin. So you can have this. What is a large temperature? Given a Fermi energy. Well, that's about the conversion, right? So this is really useful and a good number to keep in mind. All right. And let's talk about the density of states for the electron gas. So what do I mean by density of states? What I mean is the number of states on a sliver between, say, k, given wave vector k, and k plus delta k. So for a given sphere in this state, in this space, k space, I want to count the number of points that lie in this little shell between K of width delta K. That's essentially what we're like to do, is the actual number of those. And of course we have to account for the spin degeneracy, because each of these points can host either up or down electrons, so there's this factor of 2. And how do we count the number of these states? Well, I know the volume of one state, right, is 2 pi over L cube, and I'm assuming here Lx equals Ly equals Lz. That's the volume of one state. And if I calculate the volume of this shell and divide by the number of one state, I have the number of points, grid points in this shell here. All right, so in the continuum limit, again, what would be the volume of a spherical shell of width dk? Would be, well, essentially 4 pi k square, which is the area of the inner sphere, times dk. 4 pi k square dk times these 2 gives me 8 pi dk here, and I have the volume over 2 pi cube. So that's the number, right? Yeah, if you want to calculate, okay, let's subtract this from the volume of this one minus the volume of this one, and you neglect the terms in delta k squared, that's what you'll get. All right, so that's the number of states between k and k plus delta k in 3 dimensions. In 2 dimensions, it's going to be different. Notice the dimensionality here plays an important point. All right, so if I then, there's an 8 here, there's the pi square coming out. This is the number of states between k and delta k, depends on the volume, of course, and it grows as k square, right? So the larger k, the more states will fit into this little shell here. So it goes with k square. Now, how does this translate into energy? So let's see that I want to count not the number of states between k and k plus delta k, but the number of states between a given energy and the energy plus delta epsilon, plus a delta, right? And this is what's usually referred to as the density of states in energy, as a function of energy, right? So let's see how this can be calculated from this expression here. So what we want to do is essentially convert this result into energy, right? So yeah, if I know the energy of these states here, which I do, right? So all these energies here at the vector k have energy Ek, which is h bar square k square over 2m star. So if I change a small change in k, in dk, will also translate into a change in energy, right? But you have now to figure out the relationship between these two. So if I differentiate this, the epsilon dk is going to be h bar square k over m star, right? Or the epsilon is h bar square k dk over m star. Simple, right? Now I use this to try to convert this state here. So let's do the calculation in the blackboard and see how it's done. So we figure that the number of states between k and plus delta k is the volume volume in real space, k square dk over pi square. So that's in this slide here, k squared dk over pi square. And we notice that if we want to calculate now in terms of energy, what we did is this 2m star. So the epsilon is h k dk over m star, right? So that's exactly what we had here. All right. Now, of course, doesn't matter. I'm counting the same states, right? So the number of states between k and plus delta k plus delta k, it has to be equal to the number of states between E and epsilon plus delta epsilon. Right? It's just the number of states in that sliver of, the sliver of this surface shell here, this spherical shell. All right, so if I do that, then the only thing I need to do is to try to convert this into energy. All right, so I know that this is V, then there's a pi square here, and now there's a k squared dk. So k times this k dk. All right. Okay. Now let's invert things here. So this is Vr pi square. K times dk is actually m star dE over h bar square. Okay. So, and what about this extra k here? Well, we can invert this, right? So this means that k is 2m star e over h bar, and this square root. All right. So this k here becomes 2m star energy. There's an h bar here, right? And this k dk comes here as m star h bar square times dE. All right. Then we do whatever is in here should be the density of states. Okay. So what's in there? So this is the number of states between E epsilon and epsilon plus d epsilon. So how do we simplify this? This is going to be a large prefactor here. There's going to be a Vr pi squared. There's going to be a h bar cube. There's going to be a square root of 2m here. There's going to be another m star here. So this m is going to be actually 3.5. But the important thing is that this is going to be a 1/2 dE. So there's going to be a prefactor. Prefactor, let's call it, I don't know, constant A. But this is going to depend on the energy as the energy times 1/2. So this is the density of states in 3D. And this density of states goes as square root of the energy. That's an important result here. So going back to the slides, here we have then that prefactor. Here I rearrange things so that they would be a little nicer. So there's 2m star over h bar square to the 3/2. But again, the important thing is that the density of states in 3D goes as the energy to 1/2 times a prefactor. Now, how would that behave in 2 dimensions? That's the question for you in the assignment. What would be the difference when you calculate these things? The number of states between k and k plus delta k, and the energy if we had the fermium gas in 2 dimensions. So this should be identical, sorry. So that's what we're going to be doing in the assignment. So disregard confinement effects and essentially calculate both the Fermi energy and the density of states in 2D and express your results in terms of m star and the density, which is going to be now the number of particles per unit of area, right? So now you have this, precisely this system here, kx and ky, and try to redo the calculations on how the Fermi energy depends on the density and how the density of states depends on the energy in 2D. All right? So that's it. See you next class.